right. Welcome to the very last Friday lecture of this semester. Gone by really fast. Yeah. So let me, oh, I didn't turn that off. Okay. So I'm just going to begin with some quick statements about the upcoming test. So you probably saw already on the announcement section what our schedule is. So test this Monday. I have the rough draft of the test done. I want to say there's like 23 questions, something like that. The majority of which are going to be multiple choice. So yeah, I will put up the equation sheet here later today. And it's going to be like every other test we've done, right? ProctorU, all that good stuff. And you'll have all day to take it. Opens up Monday, 12 a.m., closes Monday at 11:59 p.m. Same old, same old. For the for Wednesday, like I said, there's going to be no lecture, but I will be putting up an assignment that will be a take-home portion of your final exam. So that will count for a portion of your final exam, and you just need to turn it in before what, December 11th, or yeah. So Friday, December 11th at midnight, I'm going to need that document back at that time. And I'll create a turn in with that. Final exam, I'm giving you 2 days to do it. So whatever is convenient for you, Thursday or Friday. If you wait Friday night and you cannot connect through ProctorU, since I'm giving people 48 hours, I'm not going to extend into Saturday, especially since final grades are going to be due shortly after that, at the beginning of the week. So I need to work on the weekend to get all that graded, get all the final grades put in and all that. But yeah, that's where we're going from here. Are there any questions about the test? Oh, and the final exam is cumulative. There will be new information on there that we'll cover today. And then on the 30th and December 2nd, there will be new information on the final exam, but then it will also be cumulative based on what we've covered already. So any questions about the test or the final or anything? The final is December 10th or 11th. I'm giving people 48 hours to do it. So you can pick whatever time you want to do it. Opens 12 a.m. on Thursday, closes 11:59. Are we going to do a review? We are not going to be like a class review, no. So for review, we have Michael, our assistant. He will be happy to answer any questions. I will be happy to answer any questions if you want to schedule time with me, or you're looking over the material and you have questions about that. But I will most likely probably not be doing like a whole class review, just because I have to get through material to get everybody ready for Gen Chem 2. No class on Monday? Nope, because you have a test. On the 23rd, you will be taking your test, so we will not have class then. Any other questions? Yes, it's the same deal as always. Monday, test opens at 12 a.m. and closes at 11:59 p.m. All right. So where we're going to begin then is where we ended on Wednesday. So here we have question 3 of our PowerPoint from Wednesday. And so question 3, this stuff will be on the test. So I will expect you to know how to look at Lewis structures and how to recognize which Lewis structures are correct or not. And let me get in this presentation mode. So I already did A and B for us. And what I said on Wednesday, at the end of Wednesday, since we ended, I would give you time to do C, D, E, F, and G. So that's where we're going to begin. We're just going to take some time at the beginning here and do C, D, E, F, and G. And I will rewrite A and B. So try and work out these structures if you can. So that's A and B. Again, we did that on Wednesday. C, we can do the other ones, and I will give you the answers in a few minutes here. So I'm going to start doing these a little slowly here, just in case you're still struggling a little bit. Remember, what you want to do is you want to write down the Lewis structures first. So there's BR. There's O. And remember, the dots I'm putting around are electrons. They're the number of valence electrons, and you get those from the periodic table. Bromine has 7, oxygen has 6. Since we have a negative sign, we get to add one more electron. And so we have to place these molecules in such a way that they form a structure, and everything is having the octet rule. So bromine has 7, oxygen has 6. So bromine's easy because we can just make a covalent bond there. So bromine has 8 valence electrons, oxygen now has 7, which would be a problem, except we have this extra electron. So I can just give that to oxygen. And now we have 8 electrons each. So that's how the negative sign works. You get an extra electron. If it was a positive sign, that means you lose an electron somewhere. But let's go with cyanide now. So Cn is cyanide. And minus, I get one more. So here, I'm going to draw it a little different because I know how this is supposed to turn out. There, there's our carbon, and there's our nitrogen. Right? So carbon has 4, nitrogen has 5. So I make a single bond. That goes 5. It goes to 6. Make another single bond. That goes to 6. That goes to 7. Then I still have not placed my extra electron, so I'm just going to use that to bond. And that looks really bad there. So 2, 4. Whoops, I miscounted. So that should be 1, 2, 3, 4, 5, 6, 7, 8. So that's 8. That's 8. The reason I went from 6 to 8 there is because I added an electron and then I went to bond with another electron. So if I was going to rewrite this nicely, cyanide looks like that. Again, just making sure we have octets and all that good stuff. NO2, nitrogen, 3, 4, 5, oxygen, oxygen, minus, I get 1. And so NO2. So I'm just going to rewrite the structures now kind of fast. So that will be a double bond there. That'll be a single bond. And everything now should have 8 with a minus charge. N2, H2. H. So when you have hydrogens, you usually want to put hydrogens at the end, nitrogen, nitrogen. So hydrogen will always have like one bond because hydrogen always wants a duet. So that will be there. Then I'll put my lone electrons back. So if we look, hydrogen has 2, hydrogen has 2, nitrogen 1, 2, 3, 4, 5, 6, 6, and 6. So the easiest way to solve that is make a double bond. Every time you make a bond, you gain an electron. So this is, and finally G. So G is going to be super hard. We have not seen something like G before. And the reason why it's hard is because, well, I don't know if it's hard in that the formula actually tells you how this is listed out. And that's actually one of the helpful things in chemistry once you start to read these structures. What I mean by that is the reason they write it H3COCH3 is because the molecule, the geometry actually goes CH3OCH3. So whenever you see H3C or CH3, it's going to be this group where it's carbon connected to 3 hydrogens, right? And the oxygen in the middle is connected to each carbon. And let's just check the octet rule. So each hydrogen has 2. If you have a single bond, that's 2 to the hydrogen. Carbon has 8, 2, 4, 6, 8. Oxygen has 8. Carbon has 8 here, and everything else has 2. So that is a good structure. So this question has a lot of different structures on there. And I think this is very good practice for learning how to do Lewis structures, right? And so if you can do all the examples on here, you will be have no problems looking at Lewis structures for the test. But with all of our Lewis structures written out, are there any questions or still some confusions of how I got like a specific structure, or now that you see them, can you kind of piece it out? Because I know I kind of went a little fast there for some of these, but I just wanted to have them on the paper so we can actually look at them. But now that you see them, are there any questions? And on the test, of course, you won't be writing them. You're just going to be looking at them. But any questions along those lines for Lewis structures? So just to make sure all the atoms want a full octet, hydrogen does not. Hydrogen wants a duet. It only wants 2. We're going to look at other examples today on our new PowerPoint where not everything always wants an octet. But in general, you can say yes, things generally want an octet. There are, and we're going to learn today, there are many exceptions to that, but for now we can just go with that. On E, why does one oxygen get a double bond? Yeah, sure. The reason one oxygen gets a double bond and not it is because let's look at our other structure here. So the other way to write NO2 would be like this. If I just say the double bond goes back to the oxygen. Now for this representation that I just drew here, I do have the correct number of electrons placed. However, nitrogen only has 5 electrons around it, which is incorrect. It needs to have 8. So here that would not be, or sorry, it has 6 around it. I don't know how to count. It has 6 around it, and so since that's not 8, we can't use that structure. Well, what happens if we put a double bond for both oxygens? If that's the case, now nitrogen has 2, 4, 6, 8, 10 electrons around it. That can't work. So the reason why only one oxygen has a double bond to nitrogen is so that nitrogen has exactly 8 electrons around it. It doesn't matter which oxygen has the double bond. But yeah, that's why there's only one that has the double bond there. Does that make sense? Any other questions about these structures? Where's the extra electron for E? I think I used it for the double bond. So let me just like, I'll do E again really quick. So oxygen is 6. Oxygen is 6. Nitrogen is 5. Then I get 1 electron. So nitrogen goes in the center. 1. Let's do it like that. 1, 2, 3, 4, 5, 6. Oh, it's given to the oxygen on your left. 1, 2, 3, 4, 5, 6. So double bond, single bond. And right now, this oxygen only has 7. So the extra electron goes right there to make that a full octet. And hopefully, so that is actually how I do these problems when I first try to solve them, is I write the Lewis structure, then I place them with their Lewis symbols, kind of put the geometry the way I think it's going to be based on the rules we talked about, and then count how many electrons are around everything, start forming bonds. And I usually place the extra electron last always. If I'm a negative or a -2, I will always use those last. Those are like my reinforcements, right? I send them where they need to go at the very last moment. So here I found one oxygen only had 7. So I send in my electron. Now it has 8. So the electron does not need to be displaced evenly as long as they have 8 electrons. The key is everything that have 8 electrons for right now. Yes. It's okay if and we're gonna learn how to deal with that. Like a lot of time the structures in chemistry don't have even share of electrons. But yeah, we'll talk about that today. But yes, for test 4, your mentality should be everything has 8 electrons except hydrogen has 2 electrons. Today, the material we're going to cover that will be on your final exam, we're going to learn, oh, that's like not always the case. The octet rule is not really a rule in that it's broken all the time. But for test 4, having the octet rule down is how you're going to be successful. All right, so let's move on then. Let's get to all these differences I was talking about. And what we're going to talk about today are things called resonant structures. So a resonant structure is a Lewis structure that has multiple configurations. And the way that people think about this is, well, we have that picture of the dogs, right? So a resonant structure creates what's called a hybrid, where your actual molecule is a combination of both structures. So here in our picture of the dogs, this dog is a combination of both dogs, right? It gets the white part from this dog. Looks like maybe like the face of that dog with the black spot, and a little bit longer tail. In chemistry, if you can make 2 Lewis structures that are both equally good, those are called resonant structures. And the molecule we're looking at here is ozone. So O3 is ozone. And in one Lewis structure, we have a double bond between the left oxygen and the right oxygen. In the second structure, we have the double bond between the right oxygen and the center oxygen, right? And both of those are equally good. And actually, they both exist at the same time. The actual molecule is a hybrid of both of those molecules. And what you're seeing with these dash lines, these dash lines mean partial double bonds. That is, it's kind of like a double bond, but it's not quite a double bond. It's kind of hard to like explain, but the idea is that these two resonant structures change so fast that if you were to look at it, it would be like a blur between the two, where like, you know, the double bond is kind of there, but it isn't at the same time. So the way to think about it is that these two structure 1 and structure 2 are changing so fast because they're both equally probable that the resulting structure, the real structure, is just a mesh of the two, a melding of the two, a combination of the two, whatever you want to use, so that the double bond exists in both locations at the same time. Is just not as strong as a real double bond. So that's the idea between resonant structures and a hybrid. And in reality, it doesn't actually switch, but that's a decent way to think about it. But it's really just a mesh, and that's why we have the picture of the dogs here. Like the resulting dog doesn't switch between the two parents; it just is. This real structure, this ozone, doesn't switch between my two resonant structures. It's its own entity, its own structure. And the way we decide, you know, when we have different Lewis structures, if they are good or not, is this idea of formal charge, right? And so formal charge, and I know it's cut off at the bottom, so I will rewrite those numbers when we get to it. The way you calculate formal charge is that you look at an atom, right? So here we have HCN. And you just count out in the actual Lewis structure, how many number of valence electrons do we have? Well, hydrogen has 1, carbon has 4, nitrogen has 5. So that's where the 1, 4, and 5 are coming from. Then you look at the structure and you say, how many non-binding electrons do we have? And a non-bonding electron are these dots. So if I have electrons by themselves, those are called non-bonding electrons. So what you do is you take your valence electrons minus your non-binding electrons. So hydrogen, we have 0. Carbon, we have 0. Nitrogen, we have 2. Right? Then you count how many bonds you have, right? And you basically subtract that number. What they're doing here is they're saying that a single bond has 2 electrons. So you multiply that by 1/2 because you're sharing. Another way to do it is just say, how many lines are connected to my hydrogen? So hydrogen has 1 line connected to it. Carbon has 4 lines connected to it because there's 3 right there and 1 coming off the carbon. And then nitrogen has 3 lines connected to it. So you take your valence electrons minus the number of non-binding electrons minus the number of bonding electrons, or the number of bonds. And you do that calculation. So for hydrogen, it's 1 minus 0 minus 1, which is 0. Carbon, it's 4 minus 0 minus 4 is 0. Nitrogen is 5 minus 2 minus 3 is 0, right? And when you're trying to decide which resonance structure is the best, what you want to do is you want to find the resonance structure with the most amount of zeros. It's basically your first step. Because here, structure A, we have 3 zeros. Structure B, which just flipped the nitrogen and the carbon, the formal charge of hydrogen is 0, 1 valence electron, no lone pairs, and 1 bond. Nitrogen, it's -1. Or sorry, it's going to be +1, because we have 5 valence electrons, no lone pairs now, but we have 4 bonds connected to nitrogen. So it's going to be 5 minus 4 equals 1. Carbon, we have 4, that's the valence electrons, -2 for our lone pair, -3 for all the lines connected to it. So it's 4 minus 2 minus 3, which is -1. So hydrogen 0, nitrogen is +1, carbon's -1. So we have 2 possible structures. We're asking ourselves which one's the better structure. And that's structure A, because all of our formal charges are 0. Structure B, we have a +1 and a -1. We want to choose a structure with lower formal charges. Now, I'm sure that was kind of confusing to follow. It usually is when you listen to something and you don't do it. So we're going to practice this skill, and then we'll see. Hopefully we'll have a better understanding of it. So we're going to write Lewis structures that will follow the octet rule, and then in any resonant structures and assign formal charges. So I'm going to do A for us to show you exactly what I mean. So let's start with A, and we're going to write our Lewis symbols: carbon, oxygen, and we have 3 of those. So to save time, I'm just going to write times 3, and then -2 charge. So we have 2 extra electrons. So when you have a compound with carbon, usually carbon goes in the center. Then oxygen is going to be at either side. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. Time to do the octet rule. So let's just count out how many electrons we have. 6 on this oxygen, 6 on this oxygen, 6 on that oxygen, 4 on carbon. So if I make a double bond here, that oxygen goes to 8. This carbon goes to 6. If I make another double bond here, oxygen goes to 8. This carbon goes to 8. Then I have 2 leftover electrons I haven't placed yet. Oh, actually, sorry. I messed up that structure. I'm going to take a second to go back. I only need a single bond there. My bad. That's what happens when I do this on the fly. 7, and now 7. Now I make a single bond there. 8, 7. Now I have 2 electrons to place. 8, 8. The reason why I knew I made a mistake there is because my oxygen wouldn't have been bond to anything. So that's one resonant structure, and I'm going to rewrite it clean now. So this is one resonant structure. Our other resonant structures are simple, and it's just you move the double bond around. Okay, so those are our 3 resonant structures. Those are the 3 structures for CO3 2-. Now I'm just filling in my electrons now. All right, now we have to decide on formal charges. So carbon, and I'm going to get a new color here. I'm going to do the far right image. Carbon has 4 valence electrons, -0 lone pair electrons, or 0 non-bonding electrons, -4 bonds. So carbon has 4 lines coming off of it. So it's 4 minus 0 minus 4. So carbon has a formal charge of 0. All right, now let's do this oxygen. Oxygen has 6 valence electrons. And in this form, we have 2, 4, 6 non-binding electrons and 1 bond around it. So this has a formal charge of -1. And this oxygen is actually the same because they have the same bonding pattern. So that's -1 as well. Now let's do the double bonded oxygen. So 6 valence electrons, 4 lone pair electrons, -2 bonds is 0. And what you would find is when you did the formal charges for the other two structures we did, it's the same thing because all we're doing is moving around. And although the charges on these atoms aren't all 0, these are a good structure. So when you have a molecule with a formal charge, like CO3 -2, your charges have to add up to that. So we have 2 oxygens with a -1 charge on them. -1 plus a -1 is overall -2, which is the same as our molecular formula. So I know I did it right. Your formal charges have to equal your molecular formula. So question, do I want the lowest formal charges or more zeros? Generally, the more zeros, the better. If everything cannot be zeros, like we had in the CO3 structure, you want the lowest numbers after that. So if I could make CO3 with all zeros, that would be great, but that's impossible because it has a -2 charge. So I have to make sure that my formal charge is equal -2. And when I do that, I want to be seeing ones. I don't want to see like a +5 and a -7, right? That would mean something went really wrong. So if your formal charges aren't 0, you want to try and make them as small as possible. Right. So with that, what we're going to do for the rest of the time today is just try and do B and C. See if you can figure out the resonant structures for B and C, and see if you can figure out this idea of assigning formal charges for B and C. So I'm going to give you, 4 or 5 minutes to work on that, and then I'll come back and give you the answers, show you how that's worked out. If you have questions along the way, feel free to let me know. So hopefully you had some time to work on B. So there's all my electrons for NO2. So let's just write out our skeletal structure and give the electrons back where they belong. And we already did NO2 earlier today. Now we can talk about it in a little bit more in depth. So I gave my electrons back and I'm still holding this one in reserve. So 6, 6, 5, make a bond there, 7, 6, make a bond there, 8, 7, make a bond there, 8, 7, and give my extra electron to that oxygen to make that a complete 8. But like we said, this has a resonance structure. Now let's count the formal charges. So for this oxygen on the left, it has 6 valence electrons to begin with. It has 2, 4, 6 electrons around it minus 1 bond. So overall that has a -1 charge. Nitrogen starts with 5 valence electrons around it, has 2 lone pair electrons, 3 bonds, which is an overall charge of 0. This oxygen starts with 6, 4 lone pair electrons minus 2 bonds, 0. And the other structure is the same because all we did was switch the double bond. And that's fine. That's a fine structure because overall the formal charges are equal to -1. Any questions about NO2, how I did that, how I did any of those calculations? All right, so let's do ClO3. ClO3, and I'm actually going to clear all this. So I need some room to work here. ClO3 kind of breaks every rule we talked about in that we have a halogen, but this halogen is going to be at the center of our structure. And usually a good rule of thumb is when you have one molecule connected to multiples of the same molecule, this one molecule will be in the center. Also, if it comes first in the formula and it's not hydrogen, a lot of the times that's going to be in the center too. So our skeletal structure looks something like this. 7, 6, 6, 6. All right, so we need to start making bonds. 7, 8. So this is going to seem weird, what I'm about to do. And it's something that happens rarely, but can happen, in that right now I need to start giving oxygen more electrons, but chlorine already has 8, right? Well, chlorine and anything that has access to d orbitals breaks the octet rule. So I did say obeys the octet rule. So I'll show you how to write this structure and then obeying the octet rule. And then I'll show you like the real structures. So to make this obey the octet rule, what we actually need to do is we need to start just giving electrons away. And this This doesn't really happen all that often, but it can happen. So what I'm showing here is that an electron just kind of goes to oxygen and goes to the other oxygen. Again, this is super rare, but it does happen sometimes. So basically chlorine just gave 2 electrons away without making a bond. So oxygen went to 7, oxygen went to 7 here, and this chlorine went down to 6. So now I can start doing single bonds again. So if I make a single bond here, chlorine goes up to 7, that oxygen goes up to 8, make another single bond, 8, 8, and then I have one more left to place, so I have to give it to this oxygen, so it will be the 8 as well. That's a really weird structure, ClO3 minus, the way I drew it, and I'm going to redo that so it's cleaner. Looks like this. Yeah, so I did not expect people to actually get this one. This one's really hard. So if you got it, and it still has a lone pair there. So if you got it, kudos. If you didn't, don't feel too bad because this structure is really weird. So we have this structure. Let's count the formal charge now. So chlorine starts with 7. I have 2 lone pairs of electrons, and I have 3 bonds. So overall, the formal charge is 2. And then each oxygen, so I'm only going to do this once because they're the same. This oxygen has a charge of valence electrons of 6, 6 non-bonding electrons, 1 bond, -1. So the formal charge for chlorine is 2. All the oxygens are -1. Add it all up together, that's overall a charge of -1 is what we want. Now, time's running out, but I do just want to show you the real structure, and we'll talk more about this on, I guess, November 30th, when I next see you for class. But anything that has access to the d orbital, the octet rule doesn't mean anything to it. So the real structure, if we were to look at this molecule, would look like this. And if we look, chlorine, and chlorine also has a lone pair. Chlorine has 2, 4, 6, 8, 10, 12 electrons around it. And the only reason it can do that is because on its position on the periodic table, it's right next to where the D block starts. And so it gets to put extra electrons in that D block. However, like I said, we will talk about this extensively, like in our last 2 lectures. So if you could do A and B, that's what I really expect for you out of Gen Chem 1, to do A and B and get the resonant structures. C is our challenge problem. If you can do C, then you're like at the very tippy top of Gen Chem 1 students. If you couldn't, no worries. I could not do C as a student, so no worries about that at all. But I will need you to be able to do A and B when it comes to the final exam. And like I said, this is going to be on the final exam, not on test 4. But any questions about anything before I let you go for the weekend? There will be homework up for this, but it's due on Wednesday. Yep, so the homework for this is not due on Sunday, it's due on Wednesday. And that was in the announcement as well. All right, if there's no other further questions, just one final reminder, you have 2 homework assignments due on Sunday. They relate directly to the test, so doing those is a way to study for the test. You will have another homework assignment on Wednesday that relates to this new information. Just make sure you do that on Wednesday. I will probably send out another reminder on Wednesday since, this is the first time we've ever done a non-Sunday homework. exam on Monday. I will put the equation sheet up later today. Otherwise, if you have questions on the exam, the material, let me know. Otherwise, good luck, study hard, and I will see you. Next time we'll have a lecture is in November 30th, 10 days from now. Take care and be safe during this holiday break after the test. All right.